Welcome to today's deep dive. If you are joining us right now, you likely have a vested interest in the actual mechanics of modern enterprise networking.
Yeah, you're not here for the basics.
Exactly. Today, we are pointing our analytical lens at a highly specific, strictly technical set of source material. We are looking at a rigorous practice exam for the Fortinet NSE5 certification.
Right, specifically the Fortinet and SD1 7.6 Core Administrator exam.
It's a mouthful, but it's so important.
It is a critical credential, truly a major gatekeeper. This certification is what separates the pack for network engineers and security professionals who are tasked with designing and managing infrastructure for distributed workforces.
Keeping everyone connected and secure.
Exactly. It is not just about making packets move from point A to point B anymore. It's about making intelligent, secure routing decisions at scale.
Right, and let us lay out the context of the source text here, because if you were sitting down to take this actual exam, you're looking at a 65-minute English language test. It consists of 30 to 35 multiple choice and multiple select questions.
Which is fast.
Yeah, you have less than 2 minutes per question to demonstrate your absolute mastery of FortiOS. So our mission for this deep dive is to heavily focus on 10 specific practice questions from this exam.
But we aren't just reading a quiz.
No, we are entirely tossing out the multiple choice format. We aren't going to read you a list of options to memorize. We're going to extract the core networking scenario each question presents and, analyze the engineering logic behind the correct solution.
That is the right approach. Mastering these concepts means understanding how modern networks execute that incredibly delicate balance between high-throughput performance and ironclad zero-trust security.
It's a tightrope walk.
It really is. Because if an administrator misconfigures these environments, they either introduce crippling latency for the users, or worse, they leave the perimeter wide open.
Okay, let's unpack this. Let's start with diagnosing network health, which is the focus of the very first scenario we pulled from the exam.
The foundation of SD1.
Right. So question 1 asks how an SD-WAN service level agreement, or SLA, actually determines the health and quality of a member link.
And this is where they try to trick you.
Yeah, the exam tries to throw you off by offering distractors like physical port speed or device hardware versions or hostname resolution time. But the core concept it tests is your understanding that an SLA relies on measuring network jitter and latency. That's the correct answer.
Because physical port speed is completely irrelevant to actual link health.
It's just a theoretical ceiling. I can have a 10 gigabit interface, but if the upstream provider has a massive routing loop, my throughput is effectively zero.
Exactly.
Yeah.
FortiOS does not care about the physical medium's theoretical capacity when it comes to SD1 link health. It cares about the real-time functional state of the overlay and underlay networks.
So it's looking at the actual traffic.
Right. By evaluating latency, which is the round-trip delay of a packet, along with jitter.
Which is the variance in that delay.
Correct. Jitter and packet loss. The SD1 engine uses those to build a dynamic profile of linked quality. If those metrics exceed the configured SLA thresholds, the FortiGate knows the link is degrading.
And it can take action.
It can actively pull sessions off that interface before the user even notices a drop in application performance.
Which is brilliant, and it leads directly into question 2. Because how does the system actually measure those real-time conditions without crippling the network with synthetic test traffic?
The passive probes.
Yes. Question 2 tests your knowledge of the passive probe mode in an SD-WAN health check. The options give you things like generating continuous synthetic traffic or requiring a hardware probe, but the correct answer is that it monitors actual user traffic.
What's fascinating here is the massive optimization this provides.
Why so?
Well, in a traditional active probe setup, the router generates continuous synthetic ICMP pings, or HTTP requests, to a beacon server.
Just constantly pinging to see if the lights are on.
Exactly. That guarantees a steady stream of telemetry. But in a high-density branch office, constantly generating that synthetic traffic across multiple IPsec tunnels, it consumes valuable bandwidth and CPU cycles.
But if we use passive probes, we are just looking at the TCP sessions that are already crossing the wire, right?
Precisely.
We can look at the sequence numbers and the acknowledgements to calculate the round-trip time and infer packet loss without generating a single extra packet.
You are analyzing the live application traffic. However, this does raise an engineering challenge, which is why understanding this mode is on the exam.
What's the catch?
Think about it. If you're entirely reliant on passive monitoring, what happens when a link is completely idle?
Oh.
If no user traffic is traversing a backup circuit, The FortiGate has no TCP ACKs to analyze, meaning its SLA metrics for that link go stale.
So if I configure a link purely with passive probes, and it sits idle for 3 hours, and then my primary link fails.
The SD-WAN engine might blindly route traffic to a backup link that actually went offline an hour ago.
But the router didn't know because it wasn't actively testing it.
Exactly. That is the edge case network engineers must design around. Passive probes are incredibly efficient for actively utilized links, but for idle or backup links, you often need to implement a hybrid approach or fall back to active probing.
Just to ensure the routing table has accurate, up-to-the-second state data.
Exactly.
Okay, let's move into how those routing decisions are made once we have that health data. Question 3 focuses on the lowest cost SD-WAN strategy.
This is a classic one.
The question asks how the system selects a link if multiple member interfaces successfully satisfy the SLA requirements. Options are highest bandwidth, equal distribution, shortest distance, or the correct answer, lowest configured cost value.
So we are setting an administrative distance, essentially a static integer, on each link.
Yeah, the administrator assigns a cost value to each interface. For instance, you might assign a low cost of 10 to a standard broadband internet connection, and a higher cost of 50 to a premium metered MPLS circuit.
That makes sense for budget reasons.
But here's where I want to push back on this strategy, and why I think it's heavily tested. The system validates that both the broadband and the MPLS meet the SLA, let's say, under 50 milliseconds of latency.
Okay.
Since the broadband has the lower administrative cost, it gets all the traffic. But what if that broadband link is incredibly volatile?
It's flapping.
Right. What if it's currently at 45 milliseconds, so it technically passes, but it's wildly spiking, whereas the MPLS is sitting at a rock-solid 10 milliseconds? Aren't we risking a terrible user experience just to favor the statically configured lower cost?
That is the exact risk of the lowest cost strategy, and is why administrators must define their SLA thresholds with extreme precision. The strategy assumes that as long as the SLA target is met, the application will function flawlessly.
It doesn't care who is in first place, just who crossed the finish line.
Exactly. It intentionally ignores the delta between the links. If your VoIP application genuinely requires less than 20 milliseconds of latency to sound clear, you cannot set your SLA threshold at 50 milliseconds and rely on lowest cost. The FortiGate is doing exactly what it was programmed to do, picking the cheapest path that clears the bar you set.
That makes the contrast with question 4 very stark. This one asks about the best quality strategy. When all links meet the required SLA, how does the best quality strategy determine the preferred link?
And the answer is the best measured performance metric.
Right, it dynamically selects the link with the best measured performance metric.
This completely flips the logic of the previous strategy. Best quality ignores your administrative cost tiebreakers. Instead, it looks at the real-time telemetry,
Latency, jitter, packet loss.
and available bandwidth. It plugs them into a weighted formula that you define and actively shifts traffic to whichever link is currently performing the best mathematically.
But there has to be a computational cost to that, right? If the FortiGate is constantly calculating quality scores for every single session and micro-adjusting routing paths, that seems like a massive CPU overhead compared to just checking a static cost value.
It absolutely is.
Furthermore, if two links are highly competitive, won't the traffic just constantly flap back and forth between them every few seconds?
You have hit on the exact architectural concerns. Yes, it consumes more resources, which is why you typically reserve the best quality strategy for latency-sensitive traffic like real-time video or voice.
You wouldn't use it for background server backups.
Never. And regarding route flapping, FortiOS utilizes dampening mechanisms. It won't switch sessions based on a 1 millisecond fluctuation. There are hysteresis thresholds built into the algorithm.
So it has to be consistently better for a while.
Exactly. A link must be demonstrably better by a certain margin for a certain period before the SD-WAN engine will repopulate the session table and move the traffic.
That is a crucial distinction. Okay, let's pivot from routing logic to architecture, specifically looking at the integration of Secure Access Service Edge, or SISAS.
This is where the landscape is really shifting right now.
Definitely. Question 5 asks a fundamental topology question. When integrating FortiSAS with the corporate SD-WAN hub, how is the FortiSAS instance logically represented within the network fabric?
It operates as a spoke member.
Right, C, spoke member, not a standalone bridge or a secondary hub.
Understanding this topology is vital. In a traditional hub-and-spoke SD-WAN deployment, your corporate data centers act as the hubs, and your physical branch offices are the spokes.
Pretty standard.
But when you introduce FortiSaaS into this mix to secure your remote, work-from-anywhere users, you don't build a separate isolated network. You integrate the FortiSaaS points of presence as additional spoke members connected to your central hub.
So mechanically, the FortiSaaS cloud infrastructure is establishing IPsec tunnels back to the corporate FortiGate hub
Yes,
and utilizing BGP to exchange routing tables, just like a physical branch office router would.
exactly. This overlay design means the central SD-WAN hub retains complete control plane authority over routing policies. Remote users connect to the FortiSaaS cloud, their traffic undergoes deep security inspection, and then, because FortiSaaS is just another spoke in the routing table, the traffic seamlessly flows into the corporate network.
It prevents administrators from having to manage two entirely disjointed routing environments.
It unifies the edge.
Here's where it gets really interesting, because question 6 is a major one about what happens inside that SASE environment.
SSL inspection.
Yes. It asks what is required of endpoint devices when deploying SSL inspection in a FortiSaaS environment. The distractors are things like disabling local antivirus or requiring a specific mobile OS. But the correct answer is B, a trusted security certificate must be installed.
This is a fundamental concept of deep packet inspection, or DPI. Today, the vast majority of web traffic, including malware command and control traffic, is encrypted via TLS.
You can't secure what you can't see.
Exactly. If the FortiSaaS engine only looks at packet headers, it is completely blind to the payload. To execute its security function, FortiSaaS must operate as a transparent proxy. It intercepts the user's HTTPS request, decrypts it, inspects the payload for threats, re-encrypts it, and forwards it to the destination server.
But wait, the whole point of public key infrastructure is to prevent unauthorized man-in-the-middle decryption.
Right.
If FortiSaaS intercepts and decrypts my connection to a banking site and signs the re-encrypted packet with its own certificate, my web browser is going to instantly detect a certificate mismatch.
It will.
It will drop the connection and throw a massive fatal security warning saying the connection has been compromised.
That is exactly why the exam tests this requirement. To facilitate transparent DPI without triggering browser security alerts, the enterprise must deploy the FortiSaaS Inspection Certificate Authority, the CA, to the trusted root certificate store of every endpoint device.
Oh, I see.
Typically, administrators handle this at scale, using mobile device management or Active Directory group policies. Once the endpoint's operating system natively trusts the FortiSaaS CA, the decryption and re-encryption process happens seamlessly in the background.
But if you fail to deploy that certificate,
Your deployment fails the moment you turn on deep inspection. Every user gets a security error.
that really underscores the necessity of having control over the endpoint itself, which ties perfectly into question 7.
Endpoint compliance.
Right. The exam tests the primary objective of a FortiClient endpoint compliance check. And the correct answer is D, to ensure specific security posture requirements. We aren't just authenticating the user's identity anymore, we are authenticating the state of the machine.
If we connect this to the bigger picture, this is the execution of Zero Trust Network Access, or ZTNA. It is no longer sufficient to verify that a user has the correct username, password, and multi-factor authentication token.
Because what if they do, but their laptop is infected?
Exactly. If that user's machine is compromised with a keylogger, granting them access is a catastrophic failure. FortiClient acts as the telemetry agent on the endpoint. It continuously evaluates the device's posture against configured rule sets.
So we're talking about the FortiClient checking specific registry keys, verifying that critical OS patches are installed.
Ensuring the corporate antivirus is actively running with the latest definitions.
Or even checking if the machine is currently joined to the correct Active Directory domain.
Exactly. And the real power of this system is its dynamic enforcement. If an engineer disables their endpoint firewall to test a local script, their security posture instantly changes.
Boom, access gone.
Yes. FortiClient updates the ZTNA tags for that endpoint, and the FortiSaaS Edge instantly revokes their access to sensitive corporate applications. The access is conditionally tied to continuous compliance.
That's incredibly strict. Let's shift from endpoint control to edge visibility. Question 8 asks about the main function of ingress geofencing in a FortiSaaS environment. The answer is straightforward. D, to restrict access based on geographic location. But the engineering implications of doing this at the ingress point are huge.
They are. Geofencing relies on continuously updated IP reputation databases maintained by FortiGuard. When an administrator configures a policy that outright blocks incoming connections from specific geographic regions where the organization has zero business operations, they're drastically reducing their attack surface.
And from a resource perspective, dropping traffic at the ingress interface based on a geographic IP block is incredibly cheap for the CPU.
It's the most efficient block you can do.
Right. It is much more efficient to just drop the packet immediately at the edge rather than letting a known hostile connection establish a full TCP handshake, eating up session table memory, just to have the deep packet inspection engine eventually block the payload. Geofencing acts as an incredibly efficient first layer of defense.
That is a highly accurate assessment of the resource management aspect. It protects both the network from compromise and the hardware from resource exhaustion.
Now, what happens when we don't have the luxury of installing FortiClient to manage all this?
Unmanaged devices.
Yeah. Question 9 tests your knowledge of agentless onboarding. It asks which onboarding method allows access to web resources via FortiSaaS without installing an endpoint agent. The tested answer is D, secure web gateway browser configuration.
Because while full-tunnel IPsec deployments with ZTNA agents are the gold standard for corporate-owned devices, network engineers frequently deal with unmanaged devices. Think of third-party contractors, temporary guest users, or bring-your-own-device policies.
Where installing deep-level security agents is either legally or technically impossible.
Right. You can't force a contractor to install a root certificate and telemetry agent on their personal machine.
But those users still need to be subjected to corporate web filtering and security policies if they are accessing your data. So how does the Secure Web Gateway, the SWG, actually enforce this without an agent?
It relies on explicit proxying. Instead of intercepting traffic at the network adapter level like a full-tunnel client would, the administrator configures the user's web browser to explicitly forward all HTTP and HTTPS traffic to the FortiSaaS gateway.
How do they do that?
This is typically done using a proxy auto-configuration or PACK-up file. The browser reads the PACK file, realizes it needs to send web requests to the SASE node, and the node then applies the web filtering, anti-malware, and application control policies before forwarding the traffic to the internet.
So it isolates the security enforcement strictly to the browser's traffic, leaving the rest of the user's operating system completely untouched.
It is an elegant workaround for unmanaged environments.
Okay, let's bring this home with our final exam scenario, question 10. This one is pure troubleshooting. If an administrator needs to identify which specific SD-WAN rule directed a traffic session, which log information is most relevant?
Logging is everything.
It is. The exam wants you to know that you must look for the SD-WAN rule name or identification number in the logs. That's answer C. It's not the destination port or the source hardware address.
In an enterprise environment, a FortiGate might have dozens of overlapping SD-WAN policies. You have rules routing traffic based on application signatures, rules based on lowest cost, rules based on best quality, and rules utilizing dynamic BGP routing updates.
It's a massive routing matrix.
Exactly. So when a user submits a ticket complaining about asymmetrical routing or extreme latency on a specific database query, looking at the destination port or the source MAC address in the logs tells you absolutely nothing about the policy logic.
Right, because the port just tells you it was HTTPS traffic. It doesn't tell you why the FortiGate decided to shove that specific HTTPS session out of the backup LTE connection instead of the primary fiber link.
Precisely. By capturing and forwarding traffic logs to a centralized platform like FortiAnalyzer, engineers can query this specific session and look at the rule ID or UUID that the FortiOS engine actually matched.
You have to see the router's map.
This raises an important question about visibility. Without being able to trace the exact policy that governed a forwarding decision, debugging a complex, multi-path SD-WAN environment is effectively impossible. You must have the paper trail of the router's internal logic.
Thank you all for joining us on this deep dive. We hope unpacking the engineering logic behind these scenarios gave you a sharper, more technical perspective on how modern FortiSaaS and SD-WAN architectures actually operate in production.
Keep testing those theories.
Until next time, keep analyzing the architecture, keep exploring the metrics, and goodbye for now.